Hi, my name is Jonathan Gamble, and I lead the Estimation Search and Planning Research Group at the Oxford Robotics Institute. Today I'd like to speak a little bit about our work towards metric multi-motion estimation. The past 10 to 20 years has seen significant progress in robotics. The majority of this progress has been focused on relatively simple problems. These are problems where the robot itself is simple, or the robot operates in an environment that's either static or highly structured if it's dynamic. This includes problems like self-driving cars, which are quite complex, but operate in environments where we can make strong assumptions about how objects will move. These kind of approaches aren't going to scale very well to the next generation of autonomous robotic systems. These systems are going to be a lot more complex, and they're going to operate in environments that are a lot more challenging. These environments might be unknown, they might not be very structured, and more importantly, they might be arbitrarily dynamic. Our view is that addressing these kind of challenging problems requires reconsidering some of the fundamental techniques in robotics. And today we want to talk about our work towards measuring unstructured dynamic environments. The majority of recent work on dynamic environments has been based around tracking by detection paradigms. So these are approaches that seek to identify types of objects in individual frames and then track these objects through time by recognizing their reappearance in each frame. This prioritizes recognizing an object first and then figuring out how it moves. And it's really useful and powerful in a lot of situations, such as self-driving cars, where there's this limited class of objects we could possibly see, and knowing what type of object it is gives us a lot of information about how it could be moving. The difficulty with applying tracking by detection paradigms to unstructured dynamic scenes is these complex environments often consist of multiple motions, of objects moving in unexpected ways, or of previously unseen objects moving. We believe that these kind of challenges motivate techniques that are built up around motion estimation first and classification second, effectively saying that we want to understand how things are moving relative to us before we decide which things we need to figure out what they are. There's a rich legacy of ego motion estimation in robotics based on the visual odometry pipeline. So visual odometry is one of these great successes of robotics. It's flown on every Mars mission since the 2000s. It exists in a lot of apps on phones. It exists in most self-driving car platforms. And what visual odometry is a way to estimate the motion of the camera and therefore the motion of the robot the camera is attached to based on how a static scene changes through time. So as a robot moves through a scene, its camera can be used to detect and track features and objects. When these features are matched between individual frames, we can use them to triangulate the position of the robot over time. If some of these features happen to lie on objects that are moving, then it's going to result in measurements that are inconsistent with the hypothesis of just the robot moving. But we can reject these outliers using techniques like ransack to find only the dominant motion in the scene, and then use that to estimate the robot as it moves through what may be arbitrarily dynamic environments, getting an estimate of its motion relative to its initial position over time. So the simplified visual odometry pipeline looks something like this. Our stream of images are turned into features, which we then segment into an inlier set, which is the biggest set that describes a single motion, and the rest of the features are rejected. We then take this inlier set and use it to estimate a full SE3 estimate of how the robot has moved through time. The question is, what about all these other motions in the scene? These are all being rejected. These are all can be considering outliers. If we want to get towards multi-motion estimation, we need to find a way to generate multiple hypotheses from those outliers as well. It's intuitive to propose that we could use the same segmentation technique that we used to find the first motion to iteratively find additional motions in the outlier set. But that's a fundamentally limited approach, and it can be useful to understand why. Let's look at a toy multi-motion segmentation problem consisting of 7 different motions in the absence of noise. A single model approach like ransack is very good at identifying the dominant motion in the scene and labeling the rest as outliers. What we'd hope to accomplish by applying it recursively is that we'd be able to individually identify the remaining motions in the scene. The problem is that these algorithms find the single model that best explains the current data without any consideration of future segmentation. So for example, in the toy data here, ransack would actually find a rotation out of the screen instead of finding any one of the individual true motions. This is not only incorrect, but also precludes finding future segmentations. Multimodel segmentation is actually an active area of research in computer vision that seeks to consider multiple hypotheses simultaneously by looking both at how well individual models fit the data, but also how the different models interact with each other. An example of a multimodel segmentation algorithm is Coral, which was developed by a colleague at the University of Oxford, Dr. Paul Ameo, who's now at the University of Cape Town. Paul's used Coral to do things like find planes and LiDAR data and to extract homographies, lines, and curves from monocular images. So let's look quickly at how Coral would segment our multi-motion problem, focusing on only the outlier set left over from the first pass of ransack to make things clearer. Coral requires the segmentation problem to be posed as a graph, where edges represent the possibility that data points may be similar. It then simultaneously evaluates how well a hypothesis fits the data, how smooth that hypothesis makes the underlying graph, and how many hypotheses are necessary to label the entire data set. This allows Coral to simultaneously find the 6 different motions in our toy data, and when run on the entire data set, it'd be able to find both the predominant motion that ransack can find, as well as the individual sub-motions. At a high level, this is what we do in multi-motion visual odometry. We replace the single model segmentation of ransack in the traditional visual odometry pipeline with the multimodel segmentation of Coral. This gives us a pipeline that simultaneously identifies and estimates all the motions in the scene. In this way, MVO directly extends VO to the multi-motion estimation problem. It was part of the PhD thesis of Dr. Kevin Judd and originally appeared in IROS in 2018. Without having any prior knowledge on what objects look like, how many there are, or how they're moving, MVO is able to simultaneously segment complex multi-motion scenes, and it's also able to estimate the full SET trajectory of all of these individual motions, all from a single camera system. This means that a robot operating in a dynamic environment doesn't need to reject motions from moving obstacles, but can instead seek a hypothesis that explains both their motion and the motion of the robot itself. And in doing so, estimate the full SET trajectory of the robot and the entire dynamic scene. It's worthwhile talking quickly about flow-based approaches to estimate dynamic scenes. These techniques estimate pixel-wise velocities, but turning these individual velocities into SE3 body motions still requires solving the segmentation problem. The difficulty of this segmentation is especially apparent for rotations around the optical axis of the camera, as seen with this checkerboard. One of the advantages of building on the visual odometry pipeline is that MVO is directly applicable to different sensor modalities. We've done some preliminary tests on event-based cameras provided to us by Prophecy, and you can see the results on the right. Other than modifying the feature detection to work on events, this is the same MVO pipeline that we used on stereo data to estimate the motion of swinging blocks. Another advantage is that we can make use of new advanced estimation techniques, such as continuous time estimation. Continuous time estimation makes MVO more robust to temporary occlusions by allowing it to extrapolate estimates when there are no direct measurements. It also allows MVO to reacquire motions when they appear in the expected location without depending on appearance data. This motion closure allows for the extrapolated estimates to be improved through interpolation. Here you see occlusion-robust MVO on real-world data captures outside the Oxford Robotics Institute. You can see that MVO is able to track the piecewise rigid cyclist as they are occluded by the truck and then reacquire the cyclist when they reappear on the other side. We think MVO is an interesting and exciting approach to the metric multi-motion estimation problem, but I'd also like to speak about some of the challenges. An important question to answer is what is the correct way to quantify the performance of metric multi-motion approaches? We've been using global error of all the estimates, but odometric approaches like visual odometry are well known to have errors that grow unbounded with distance. So it's not surprising to find that when we're simultaneously estimating the third-party motion and an ego motion, that these global errors are growing quite quickly. And you can see that on the video on the right, where the box that's swinging back and forth with the green trail, it looks to be walking away even though it's actually swinging in place. And so the question that poses is global error truly the correct way? Is that actually what we care about when we're operating dynamic environments, or do we only care about the error of the objects relative to ourselves? We couldn't find a lot of research on the right ways to quantify metric multi-motion approaches when we were working on MVO. So we set out to capture a data set to help support future research in these areas. The Oxford Multimotion Dataset consists of a number of dynamic scenes where there is ground truth trajectory data as captured from a Vicon motion capture system for everything that's moving in this scene. That includes both the dynamic environment as well as the sensor rig. The sensor rig has a stereo camera, an RGBD camera, and an inertial measurement unit. And the dynamic scenes include scenes with multiple independent motions, like the swinging blocks here, motions that purposely come in and out of occlusion, like the tower and swinging block here, a number of complex scenes that are unstructured and have a number of different motions, up to 6 different RC cars being observed from the sensor rig. For all these different scenes, the data is captured in 3 different ways, one with the sensor rig completely static, one where the sensor rig mostly only moves translationally, and one where the sensor rig moves unconstrained through SE3. The dataset is freely available to everyone and is available from our website at robotic-esp.com/OMD. Anyway, thanks for taking the time to watch this talk on how we've used multimodal segmentation techniques to extend the visual odometry pipeline to the multimotion estimation problem. Our algorithm, Multimotion Visual Odometry, or MVO, provides metric SE3 estimates of entire dynamic scenes without having any prior knowledge about the nature or number of motions. If you'd like to learn more about MVO or about the Oxford Multimotion dataset, please check out our website. Thank you.